And my first question to the panelists is beyond CMOS, namely, is it the end of it, or do you think that it has still steam to take us for another 10 or 15 years? And you can relate also to Moore's law, etc. Oh, yeah. Sorry, yeah. Actually, I have their bios, and if I read the bios, then we are taking the whole time of the whole thing. But let every person introduce himself for about 30 to 50 seconds. So please.
Hi, I'm Pei-Lin Pai from Winbon Electronics. In Winbon, I'm in charge of technology development for both DRAM flash and RRAM.
Hello, everyone. My name is Ben Yehuda. I'm the CTO and one of the co-founders of Lightbits Labs, an Israeli startup. This workshop has been very interesting for me because I'm an operating systems guy. So this is about 17 layers below where I usually spend my time. So fascinating stuff.
Pankaj Mehra from Western Digital. I was CTO of Fusion IO and in Western Digital through SanDisk acquisition of Fusion IO. Before that, 14 years tandem compact HP. I was professor at IIT and worked in machine learning a couple of times in my career and wrote pieces of InfiniBand spec.
Hello, my name is Ahmed Berman. I'm from Samsung. I'm the manager of the Israeli R&D Center, focusing on flash memories and emerging memory technologies.
Hello, my name is Stuart Punkin. I was at IBM Research for 35 years as IBM Fellow, and I recently moved to become a director of the Max Planck Institute for Microstructure Physics in Halle in Germany. So my expertise is in spintronics and creating atomically engineered materials.
Thank you. So as you figured, we have here about 150 to 200 years of experience, and I hope that will show on the answers. So back to my question is, okay, is CMOS running out of steam? Is Moore's law running out of steam? And if so, what's the next thing? Or how do you see this evolving? Please give me your perspective. Who wants to start? Would you like?
Oh, I'm happy to start. I think CMOS, of course, it's a huge engine, so it will continue for many years into the future. It's, as we heard from this beautiful last talk, it's extraordinarily difficult. The technologies are really amazing, and the amount of money required to build a technology at the manufacturing scales that are needed is just simply mind-boggling. So my own, as I mentioned in my talk yesterday for spintronics, this emerging technology of magnetic random access memory, which you mentioned, is fantastic technology, which actually I proposed 25 years ago. And today it's on the verge of becoming an important technology. That means, as I mentioned, in the last 3 or 4 years, there's been about $1 billion of investment. And it still is a long way from being a real technology. So CMOS will continue for many years into the future. But I think there will be add-ons. There's a lot of opportunity to make it, to evolve it. Not only, and we can see, for example, in the last 10 years, more and more new materials have been introduced into CMOS to make it possible that it could be continued. And so I think there's a huge opportunity for new materials, new physical phenomenon, and new devices, new architectures that will play an important role in the next few years.
Okay, next. Okay.
Okay, so the answer is a little bit complex. As you know, we in Samsung already have in mass production a 3D memory device, which consists of various new devices which were published. And the answer related to the CMOS is that, as you already know, many of the CMOS transistors were replaced by FinFETs in the latest manufacturing technologies. But if I'm considering CMOS future, I can see it transforming into similar devices, but not actually CMOS. But the really cheerful and encouraging answer is that I don't see Moore's law stop. We will continue to scale, and we're scaling vertically, and successfully. And we have 64 layers in production later this year. We already have 48 layers in production, in products, in mass production. So I can gladly say that we continue to scale.
Good. Pankaj?
I'll give a quicker answer.
Speak closer to the phone, to the microphone.
So the question about CMOS is really whether you want to have compute that remembers or memory that computes. I think this conference produced the answer. And if I read the consensus of all the presenters who went before us in the last 2 days, I think the inkling of the crowd in academia is memory that computes. And I agree with that. I think this idea takes hold when we go back to old presentations from Bill Daly and others about state of state, which is the difficulty of compute that remembers is very pronounced in academic and industrial literature. But memory that computes has very promising outlook. And the world is becoming memory and data centric. So I think Moore's law continues, I think CMOS continues, but there is a need for memory that computes, and that drives us forward.
So, Rafi, with your permission, I'll skip the part about CMOS because I had to go look in Wikipedia what exactly is CMOS earlier. Exactly.
Guess what? It was born before you.
I'm not so sure, but with regards to Moore's law, we were told to disagree with each other. Unfortunately, I do agree with you guys. It will continue, but not in the narrow sense that it used to be in the past. In a broader sense, the future is hardware acceleration. So computing systems will continue scaling, but it's not going to be in the traditional single core performance that we've seen in the past. And it's not even going to be in the more recent, let's just add more and more cores to the chip. What's going to happen is that the systems will become more capable, but the way that they will become more capable is through specific hardware acceleration. And if this doesn't make sense to you, consider it at cloud scale, because that's where the interesting things are happening today. And if you ask Amazon, if you ask Google, if you ask Facebook, they will tell you when you run at cloud scale, hardware acceleration, and I'm quoting James Hamilton from Amazon here, it's not a nice to have thing, it's a requirement.
Just one comment, Muli, as I told you in the intermission, okay? The proof of the pudding is when the cloud brings rain, so we'll see.
As long as it's not acid rain.
I agree with the other panelists. I think the Moore's law will continue, but it may or may not go with the CMOS. That's the part I'm different from the other people. Because for the past 40, 50 years, the driving force for CMOS is to make a cost lower and lower. But after 20 nanometer, going down to 1, 2, 3 generation behind 20 nanometer, it's not going to get any cheaper. And from the 1X, 1Y, 1Z generation, there's other factors that come into consideration. Thermal, power, these are all become more and more important. So I'm actually seeing a lot of companies are coming out with some of the old technology, like SOI. Only with SOI, you can have operating voltage down to 0.5 volt or even lower. With the current CMOS, it's not possible. So I do see the Moore's law continue, but it may not be the same path with the CMOS.
Thank you. Going from the very, very low microns and nanometers and so on to the other end, 17th layer above, okay? The question is, what is going to be the next killer app? By the way, if you ask my grandchildren, it's the spinner. You know this thing? I mean, by far, within 3 months, everyone has one. So it doesn't need to be very sophisticated. So what do you think is going to be the next killer app for the next, let's say, 5 to 10 years?
Maybe I can start.
Sure.
So now it's been about 25 years since 28 since I published my first paper in HKI. And I've watched machine learning, we are in the second wave of major machine learning work. And if you look at, why is machine learning so popular now? 40% of every company, big or small, their compute cycles, about 40% is going towards machine learning, data science type work. And the answer is because doing things the old way, whether you are Netflix or Google or Amazon, just doesn't work. There's a very good ISCA paper called Rule of Three by Kim Hazelwood, who was at Yahoo. She did a study of 20,000 Google servers. And whether it is instruction cache misses, code complexity due to Kolmogorov complexity of program description for anthropomorphic tasks like vision, speech, search, I think the workloads that we are asking computers to do, the problems we are asking computers to solve, are driving a revolution in the technologies we are having to build. So I think the killer application is not one, it is a set of things, and they all have to do with things like artificial intelligence, context-aware computing, and goes back to search and advertising.
Muli, what do you think? This is your field.
No. Predicting the future, that's hard. So there are several fields that I could mention in addition to machine learning and AI, which I agree about. One is autonomous vehicles. Another is drones. Another killer application that I think that I'm personally the most excited about, and this actually comes from experiences that I've had with my kids. So when my kids got their first AR or VR goggles, we had to instate a rule at home that you can only use this equipment if you're actually tethered, holding on to something that doesn't move. Because my son, who was 5 years old at the time, when he put the goggles on, he was so immersed in it, and this is primitive stuff, but he was so immersed in it that he just walked around and walked into walls, okay? So personally, I think augmented reality and virtual reality, the stuff that's coming down the pipe, that's gonna be a killer app. It changes everything.
Any further? Any further comments? Yeah,
Well, certainly I cannot predict the killer app, but I can provide you with an algorithm to find it. So I noticed that killer apps recently or in the last 10 or 20 years are algorithms that were invented long ago. Maybe 20, 30, 40 years ago, maybe 50 years ago. We see many uses of algorithms that are relatively old, but they didn't have the compute power and the memory to implement it. So if you want to find the next killer app, you should open the theories, which are relatively old, and they looked very promising back then. We talked about Memristors in the 70s, that they were all theory and there was no way of implementing them. And other algorithms from the 60s that I cannot expose, but they were pretty good, but we didn't have the compute power and the enough memory to implement them. So as computing power and memory and storage are advancing in huge steps, we opening a path to apply theories that are relatively old, but we can apply it in a new way. So this is my guess for the next killer app, something that brought to life from the 60s or 70s, but now we have the ability to make it happen.
Okay, one more question before I turn to the audience. This was supposed to be more of a business and industry-oriented panel. So if I observe what happened in the past few decades, in the old days, okay, we had what we call vertical companies, namely the same company, take Intel, TI, National, Motorola. They had everything from the design to the manufacturing to the product and marketing and sales and so on. Everything was done by one company, okay? Then came the paradigm of a foundry and a fabless and so on, namely there are a lot of companies, great companies today, like Qualcomm and SanDisk to some extent, and many of the others who did not manufacture, but they only did a very specialized design and let other people specialize in manufacturing. On the other hand, because the cost of manufacturing is so huge, only very few companies could afford going down the nanometer scale. When a fab costs $5 to $10 billion, not too many people have enough deep pockets. The question is that consolidation so that only maybe 5 to 10 companies can afford a fab continue, or because of those exotic technologies and other, side ideas or whatever it is it going to change the arena as far as, the players in our industry? Please.
Let me start with that. We do see the consolidation, and actually, many years ago, we forecast that there are only 3 industries that can afford to continue to build the fab. That will be the CPU, memory, and the foundry. So you are seeing all the IDM companies going out of the manufacturing side, and this will continue. And as the number of companies gets smaller and smaller, they will be more and more competitive. I think the largest foundry company, TSMC, in the world, their biggest challenge in the future is when they go down to the sub-10 nanometer technology, there will be only a handful of customers, and there will be quite a few companies that could do that. So the competition will be extremely tough. So in that area, there will be a very tough competition, both from the business side, both from the customer, also from the vendor side. And so this will see more and more consolidation, and the value will be put into the innovation side. That is not consolidated yet.
Okay. Who else wants to?
Let's just say a little bit. I think if you look around and see where design wins are coming from, design wins for new chip designs are going to increasingly come from IoT. And IoT is looking for integration of CPU, memory. It's very SoC environment. It's very embedded oriented. And I think it's not clear who the winner is. If you look at CPU, custom masks and kitchen sink processors, that doesn't look like the winner for IoT. Memory, discrete memory, does not look like winner for IoT. And foundry, will they be able to deal with the cost structures? So I don't know. But, this is how it looks like.
Okay. Amit?
So basically, we have to figure out what happened that we're all wondering about consolidation. So I think what happened that in deep submicron lithographies, in very small lithographies, and in 3D structures, the fab investments and the cost is so high that most of the single companies, of course not Samsung, but most of the single companies found very hard to get the money for such step, moving from planar lithography to 3D structures and moving to smaller layers. But I think that once in time, this stepping stone that we have to go through, after we establish the first 3D structures, then consolidation would be needed, because consolidation was needed to get through the huge investments in changing direction from 2D to 3D. And after we are on the 3D path, until the next breakthrough or the next direction, then consolidation doesn't seem necessary, but it's all guessing, yeah. It's all an assumption.
Just one comment. 3D is good for structured, like memories. I don't think microprocessors are going to go 3D. Anyhow, okay.
I was talking about memory.
I know. Okay. Now we turn to the audience for questions. Who has a question for the panel? Okay, let's start here.
Hi. Buzz emphasized the difficulty of having a new technology. And it's obvious that all the companies are working on emerging technologies, so they think that there is something there. What is required in order to make a new technology commercial, in your opinion?
An order of magnitude improvement. That's a very simple rule of thumb.
In what?
In something. If you don't have an order of magnitude improvement, it's going to be very hard. If you do, you have a chance.
What means either performance or power or cost? Or all three of those?
So I think it's absolutely true that that and a lot of respect for the curve of technology adoption. So nothing that is new and disruptive gets adopted as quickly as we first think it will be, and nothing that is revolutionary and gets an order of magnitude improvement is ever ignored 10 years after it is invented. So I think patience at the beginning and tenacity during that 10-year period are both important in getting there. Now, I'll say one thing. I think we heard a lot of presentations, and people will forget after this meeting what Professor DiMichele said on tools, software. You know, I was there at HP Labs when they came up with the Memristor, and they hired the father of modern CAD, parallel CAD, to run HP Labs, and he failed to do any parallel CAD work. I consider that one of the reasons why Memristor did not succeed at HP, because they ended up going after memory-only market rather than doing Shahar, what you are doing now with the new memory that computes. But I think your work, for example, you know, you're looking up the tool chain. I really like that. I think that kind of software work and orchestration in optimizers that can do push-down optimization to near memory compute, these are elements besides device work and integration work that are needed for new technologies to succeed.
Can you be more specific about an order of magnitude improvement? Because I think it's not just generally an order of magnitude improvement, right? If you improve the retention time of a storage by an order of magnitude, who cares, right? 20 years, so it will be 200 years, right? But if you improve the cost by an order of magnitude, it's a different thing.
Sure, there are different metrics for different technologies, different things that are important. I spent 10 years at IBM Research, where my hobby was killing ideas while they were small. You know which ideas I couldn't kill? Those that had a promise of an order of magnitude improvement in at least one metric. Now, it has to be an important metric. As you said, if you build something that has to last a year, and existing technologies can already last for 100 years, then lasting for 1,000 years makes no sense in that market. Find another market where it does make sense. But in general, and you know, I'm being very high level here. We can talk about specific technologies, except don't ask me about CMOS because I know nothing about it. At a high level, an idea has a good chance of succeeding. Sometimes it will take 10 or 20 years if it can provide an order of magnitude improvement in an important metric.
You would like to?
Well, I would just say that I think things can change very quickly. So if you look at if you look at the dynamics of what has happened in the last 15 years, companies have been formed, Google and Facebook, that were totally unanticipated. So I think just saying an order of magnitude, it doesn't mean very much. I think the whole computing world has evolved as we've moved from big mainframe computers to the PC market. Now we're going to cloud computing. The whole market has, so the types of devices that you need and the metrics that you need are entirely different, even today, than they were just a few years ago. Cloud computing has evolved much more rapidly than IBM had anticipated, and many of us had anticipated. And so I think it's too simplistic to say you need an order of magnitude. You have to think about No, I agree with that, but I think at the same time, the world has completely changed in 10 years in ways that were totally unanticipated. So it's difficult to imagine what the world would look like in 10 years' time, when probably if the computing systems will continue to improve in performance, and it'll be cheaper to store data, and communication systems will get better, and that means there'll be entirely different applications. And so for those applications, you'll probably need systems that have different characteristics from today. And so I think you have to think entirely differently. It's too simplistic to say, let's just evolve devices in the way that they have evolved. And it's really more like today you need a system that can do something different. So I think, like, what will the world look like in 10 years' time? Nobody can predict that. All the predictions that people typically make are wrong. And looking backwards, you say, oh, that was obvious. We should have done this. So like, I think like Google is fantastic. They said, okay, Larry Page said, okay, I can digitize one book. That's what most of us would say. He had to digitize all the books in the world. And that has entirely changed the world in a space of just 10 years. And now we can't imagine living without those technologies. And so I think, I imagine that with all the creativity that is around, I can imagine that something off the chart will happen. For example, additive manufacturing, 3D printing, self-organized materials, biologically inspired materials and systems and devices. All of that, I think, will happen, and it might happen sooner than we anticipate. Would be my answer.
Okay,
yeah, I don't have a criteria what will happen, but I have an observation. I think the new material introduction into the silicon fab is going to be more and more difficult, because we used to have Yorktown High, we used to have Arlington Center. We don't have that anymore. Today, I am seeing this. We are facing more and more proprietary material, proprietary process. People are forced to reinvent the wheel. The other company has already done. So that makes the new material, the new methodology introduced in the fab getting more and more difficult.
I would like to offer you a proposal for what will be the winner. The winner is the story of Moisele and Yosele in Yosemite when the bear wakes up. The one that runs faster is the winner. You don't have to outrun the bear, you have to outrun your competitor. So that's enough to get a new technology to the marketplace. What do you think?
Was that a question? Okay.
So I would like to repeat your smart saying, to make an instant success, it takes 30 years of hard work. So I completely agree with that. And an order of magnitude is necessary, but it is not sufficient. The hard work of getting a device, and we've seen many wonderful devices operating fabulously when they have to go through arrays, they have to build the accurate array structure and periphery circuitry, and look at the complexity. I mean, 40 years ago or 50 years ago, all you needed for memory was a good device, and you put on some voltages, and that's okay. And suddenly we need this system on chip, and we need this error correction. And actually today we need many, many more IPs handling the memory for reflecting the value to the customer. And some of those IPs I can't talk about, but they are absolutely required and demanded by customers in order to make a product. So the real challenge is to bring the device to the product, and you have to consider so many disciplines on the way. Actually, it just means that you have to be smarter than 14 years ago. You don't have to come up just with a brilliant device. You have to come up with a brilliant device and understand the array structure that is optimal for it, and the periphery circuitry that is optimal, and what is the ratio of the die, and what is the IPs that around the memory, that managing it. So it has to be a complete system.
Let me comment a little bit. Everybody's trying to outrun the slowest one, but running faster than the slowest one is a good strategy. But to be the leader, the first one, it's just like the leader of the flying goose. It's very extremely expensive. From our experience, most of the experiment fail, and that can amount to a huge sum of R&D money. So, as long as there are a few parties in the team, as long as you are not the slowest one, it's okay. But try to be the leader is going to cost you a lot of money.
Yeah, I will amplify that when you are first there, being early to the market, there is nobody there to take your product. It's a really, really important thing to understand. Being too early, like 10 years early in the market, is a very, very bad thing to do. Timing is very important. I think startups are a key ingredient of success. Big companies like Samsung, they made the statement from their perspective. Unnecessary complexity, if we have it, whether in NAND business or DRAM business, we won't see it. Some startup somewhere will see it, and they can simplify when complexity is unnecessary. I'll say one more thing. If you look at NAND business, we just heard a great talk by Boaz. Look inside a modern SSD today in the data center. There is 1 terabyte per second of untapped read bandwidth in a typical SSD that is sitting today, that the best PCI interface of the next 5 years will not be able to expose. So all day we heard near data processing, near memory processing talks that are combining 2 risks. They are taking the risk of near memory computing and multiplying that with another high risk of a new memory technology. Ask yourself, why are you doing that? Why not take a stable memory technology like NAND that has untapped potential of read bandwidth, combine that with a new idea like near memory computing? This is what I am doing in my iMemory project in Western Digital CTO group. So, think about new ideas, but don't take on unnecessary complexity, unnecessary risk. I think there is a lot of opportunity, but you have to be smart about it.
Thank you. Let us move to the next question from the audience. Yes, Tzachi.
Yeah, I have 2 quick comments from nature, I guess. One is, how a mouse wins a race against an elephant, rides on the elephant's back, and the last meter hops off and gets there. That's a way for leading also, sometimes. Let someone else invest, follow, and then last minute hop there. The other thing is, which is not funny, it's philosophical. There are 2 ways to shoot down a bird. One is if you're a good sniper, aim well. The other is to aim and be lucky and have the bird fly in front of the barrel just when you press the trigger. And I'm wondering, regarding successes, what fraction of them are really good aims, seeing the future and being there in time, and which are just, like there is a lottery winner every week. We don't know who, but with high probability somebody wins. And we just see the winners and then think backward as if they designed. Not sure which one of them. Now, my question is, it was already mentioned a bit, but the intellectual property issue, I'm wondering to what extent you think that pooling together intellectual property in the memory area, for example, would have helped things along much faster, easier, both in the past and looking to the future. Because obviously, so many ingredients go in, not only in the fabs, in architecture, everywhere, that it seems that the likelihood of any one company having it all is very low. So do you think something can be done there?
Any thoughts on that? Let me give you one comment on that, okay? There is this guy who every Thursday comes to Jerusalem to the Wailing Wall and prays that he's going to win the lottery. So after a year or 2, the angels come to God and tell him, let him win one time. So he said, yes, but let him fill the lottery once at least. Okay, so it takes some effort to win also. It's not just luck. Okay.
Let me
one or
start.
2 answers, and by then we'll have to finish this panel, unfortunately, because of time. Go ahead.
Let me try to answer the IP issue. The IP issue, our current patent system is actually pretty antique. And it's actually blocking a lot of progress instead of encouraging or probably reward the inventor, especially those law firm, the non-practice entity, NPE. And there's a recent, I think, opinion from the U.S. Supreme Court, and I think that will change that a little bit. But up to now, people are still trying to protect their know-how. This is their competitive advantage, and it's very difficult. Just look at the JEDEC, all this standard setting committee, and there are companies with strong patent portfolio, and they elected not to join it just to protect their IP. So it's really going to be done.
Okay. I think we'll stop here. One more philosophical comment. I work at least 3 companies that were leaders in their field, Intel, NDS, and Given Imaging. In all 3 cases, it wasn't luck. It was a lot of hard work, but a lot of systematized, I would say, leadership that led to where they were, and all of them were leaders in their field. One more comment, Boaz. I also transitioned from semiconductor to medical devices. And I would say medical devices is even more complex. Not on the technology. Regulation, reimbursement, you name it. I mean, a lot of headache. Anyhow, so thank you very much for the panelists. Give them a hand. And I would ask A.B. Friedman to come and say some concluding word for the whole workshop. Thank you very much. Thank you.
Well, it's been a very busy couple days. There's a lot of great people in the room. I think we all recognize that. We have learned a lot from each other. And it's been a real privilege, actually, for me, and I think for many people here, to enjoy the company of the people in the room. So I really want to thank our special keynote speakers, the many talks we heard over the day, and actually everybody in the room, because we all participated in our own fashion. The posters were nice. I mean, there was a nice half a dozen posters out there. Actually 25, I think, with the total number. I really want to thank everybody, but let me start off by mentioning that Laraz, wherever you are, she's the heart and soul of what made this happen. I want to thank her very much. Avi Noam, where are you? Are you hiding? You're always hiding. Avi's still hiding back in the corner. And the person who truly did the most work, and I really want to express my appreciation, is Shacha. So, you know, having a email exchange with everybody in the room times 10 takes a hell of a lot of time. And Shacha did that, and you have to really give him credit. This was an important meeting, a workshop, not just for the Technion, but also, I think, for the community. So hopefully something bigger and better will come out of it. So again, I want to thank everybody, and once again, safe travels home, take it easy. If you miss a flight's okay, just be safe. Take care, bye-bye.